Welcome to an exploration of how interdisciplinary approaches revolutionize problem-solving in science and engineering. Interdisciplinary science combines multiple fields like physics, biology, and chemistry to tackle complex problems that no single discipline can solve alone. Let's begin by understanding what makes an approach truly interdisciplinary. Interdisciplinary science integrates knowledge, methods, and perspectives from multiple scientific domains to address complex challenges. The synergy between disciplines creates innovative solutions that go far beyond what any single field could achieve independently. Multiple disciplines contribute their unique tools and perspectives, converging on a unified solution that leverages all their strengths. Why has interdisciplinary science become essential in modern problem solving? Let me pose a question. Why can't a single discipline solve all problems on its own? The answer is that real-world problems are inherently complex and multifaceted, requiring diverse perspectives and methodologies. Consider climate change. It requires atmospheric physics, environmental chemistry, ecosystem biology, economic modeling, and policy analysis all working together. Climate science is a perfect pyramid of interconnected layers, where each level depends on understanding all the others below it. Let's examine how MRI technology exemplifies interdisciplinary engineering at its finest. Magnetic resonance imaging beautifully combines nuclear physics, quantum chemistry, computer science, and medical knowledge. The fundamental equation is omega 0 equals gamma times B 0, where omega is the Larmor frequency, gamma is the gyromagnetic ratio, and B 0 is the magnetic field strength. With typical clinical values of 1.5 Tesla magnetic field strength and proton gyromagnetic ratio of 42.58 MHz per Tesla. This gives us a Larmor frequency of approximately 64 MHz, which is in the radio frequency range. The magnetic field aligns hydrogen protons in the body. Radio frequency pulses then perturb this alignment, and the return signal is measured and processed. Ask yourself, what specific disciplines are essential for MRI to work? Physics provides the nuclear magnetic resonance principles and signal detection methods. Engineering designs the superconducting magnets and radio frequency coils with extreme precision. Computer science develops sophisticated algorithms like Fourier transforms to reconstruct images from raw signal data. And medicine provides the knowledge to interpret tissue contrast and make accurate diagnoses. Now let's explore the mathematical framework that enables interdisciplinary integration. The MRI signal as a function of time combines exponential decay physics with oscillatory behavior expressed as S of t equals S0 times e to the negative t over t2 times cosine of omega 0 t plus phi. T2 relaxation time is typically 50 to 100 milliseconds for biological tissues, determining how quickly the signal decays. Here's the signal decay showing the characteristic exponential envelope modulated by the Larmor frequency oscillation. The final image is obtained through inverse Fourier transform of the k-space data, written as I of xy equals f inverse of s of kxky. This single equation bridges signal processing theory from electrical engineering with spatial imaging requirements from medicine. Biomedical engineering represents perhaps the ultimate integration of disciplines. It seamlessly combines biological sciences, medical knowledge, physics principles, chemistry, and multiple engineering disciplines. Consider artificial heart valve design as a perfect example of this integration. An artificial heart valve must handle blood flow dynamics, minimize turbulence, prevent clotting, and withstand millions of cycles. The Reynolds number equals density times velocity times diameter divided by viscosity, determining flow regime. For blood, density is approximately 1060 kilograms per cubic meter, and viscosity about 0.004 Pascal seconds. With typical aortic flow velocity of 0.5 meters per second and diameter 25 millimeters, Reynolds number is approximately 3,300, indicating transitional flow. Engineers must simultaneously consider fluid dynamics for efficient flow, material biocompatibility to prevent rejection, and mechanical stress analysis for durability. Environmental engineering demonstrates integration at global scales. Modern water treatment combines chemical processes, biological systems, and civil engineering infrastructure. Contaminant decay follows first-order kinetics. C of t equals C0 times e to the negative kt, where K is the decay rate constant. For chlorine disinfection, decay rate is typically about 0.1 per minute. Time for 99% removal is natural log of 100 divided by K, giving approximately 46 minutes. Water flows through multiple treatment stages, each requiring different scientific principles working in sequence. Renewable energy systems exemplify how technical and social sciences must integrate. Solar panel efficiency depends on quantum mechanics describing photon absorption and materials science optimizing semiconductor properties. Efficiency ETA equals output power over input power, which is open circuit voltage times short circuit current times fill factor divided by solar irradiance times area. Typical commercial panels have open circuit voltage 0.6 volts, short circuit current 9 amps, fill factor 0.8, and area 1.6 square meters. With solar irradiance of 1,000 watts per square meter, this gives efficiency of about 20%. Incoming photons excite electrons in the semiconductor, generating electrical current through the photovoltaic effect. However, successful deployment also requires economic analysis, electrical grid integration expertise, and supportive policy frameworks. Nanotechnology operates at the intersection of physics, chemistry, and biology at molecular scales. Why is interdisciplinary thinking absolutely crucial when working at the nanoscale? Because at these tiny scales, quantum mechanical effects dominate, and classical physics rules completely break down. The de Broglie wavelength lambda equals Planck's constant h divided by momentum p, which is mass times velocity. For an electron moving at 1 million meters per second, the wavelength is approximately 0.7 nanometers, comparable to atomic dimensions. At nanoscale dimensions, materials exhibit quantum properties like electron tunneling and size-dependent optical properties. Carbon nanotubes are created through chemistry, but understanding their extraordinary mechanical and electrical properties requires quantum physics. Their Young's modulus reaches 1 terapascal, that's 1 trillion pascals, making them among the strongest materials known. Artificial intelligence now serves as a powerful interdisciplinary tool across all sciences. Machine learning dramatically accelerates drug discovery by predicting molecular interactions and properties. This combines organic chemistry knowledge, biological understanding, computational algorithms, and statistical analysis. The loss function for binary classification is negative sum over all samples of yi log pi plus 1 minus yi log 1 minus pi, where theta represents model parameters. Neural networks process molecular features through hidden layers to predict drug activity, learning complex chemical relationships from data. AlphaFold recently solved the 50-year-old protein folding problem, combining deep learning with decades of biochemistry knowledge. Systems engineering provides the framework for managing interdisciplinary complexity. Systems engineering takes a holistic view, considering how all components interact rather than optimizing parts in isolation. All system components are interconnected. Changes to one component propagate through the entire network of relationships. Spacecraft design perfectly illustrates systems engineering, requiring coordination across dozens of engineering specialties. The rocket equation, delta V, equals exhaust velocity times natural log of initial mass over final mass governs mission capability. Reaching low Earth orbit requires delta V of approximately 9.4 kilometers per second, demanding mass ratios around 20 to 1. Success demands integrating propulsion systems, structural engineering, thermal control, power generation, communication systems, and more. Effective interdisciplinary work requires overcoming communication barriers between fields. The challenge is that each discipline has developed its own specialized language and underlying assumptions. The solution is developing shared vocabulary and creating conceptual bridges that translate between disciplines. Building conceptual bridges between disciplines creates overlap regions where specialists can communicate and collaborate effectively. Mathematical modeling often serves as a universal language that all scientific disciplines can understand and use. The future of science and engineering is increasingly interdisciplinary. Convergence is accelerating as boundaries between traditional disciplines become increasingly blurred and irrelevant. The grand challenges facing humanity, from climate change to pandemics to energy, all require deeply integrated approaches. While traditional single-discipline research remains constant, Interdisciplinary collaboration is growing exponentially year over year. Emerging fields like synthetic biology merge engineering principles with molecular biology to design living systems. Quantum computing unites quantum physics, computer science, and advanced mathematics to create revolutionary computational power. Let's conclude by reflecting on the transformative power of interdisciplinary integration. Complex real-world problems demand diverse perspectives that no single discipline can provide alone. The integration of different fields creates innovation and breakthrough solutions that transcend individual disciplines. Multiple disciplines connect through a central solution hub, where all perspectives converge to solve problems no single field could address. The future of science and engineering belongs to those who can think across disciplines, integrating knowledge to solve humanity's greatest challenges.